my last lecture, I spoke about squeezed light, among other things, and I showed that squeezing is a very interesting property peculiar to the quantum world, where it's possible that the variance in x, for instance, of the observable x in a certain state, which would be the squeeze state, is less than half if we work with units where the Planck's constant is set equal to 1. I want to consider some more interesting quantum superpositions of the photon number states, for instance, in today's lecture. In particular, I want to talk about an infinite superposition of photon number states, a very particular infinite superposition of photon number states. That's called the coherent state of light. Ideal laser light is an example of a coherent state. Therefore, today I will talk about coherent states. Just for recapitulation, in quantum optics, n would be the n photon state, ket n would be the n photon state, which means n, the label n, is the number of photons in the state, so that n can take values 0, 1, 2, and so on. The Hamiltonian under consideration is a dagger a plus half h cross omega, half h cross omega being the 0 point energy, and omega being the frequency of the radiation field. Radiation field is the quantized electromagnetic field. A and a dagger are the photon destruction operators and creation operator respectively. And they satisfy the algebra, the commutator algebra. A dagger is equal to 1, where 1 stands for the identity operator. I work with units h cross equal to 1, possibly omega equal to 1. Just for convenience, we can always put back the h cross and the omega using dimensional arguments. Now I consider the superposition ket alpha. Alpha is any complex number given by some normalization constant n, which we will find out. So this is an infinite sum. It has the 0 photon state, the 1 photon state, the 2 photon state, and so on. So we have an infinite superposition of photon number states, and the weight is different. It's alpha to the power of n by root n factorial, corresponding to ket n. First of all, let's normalize the state. I want this property, alpha alpha is equal to 1, the inner product is equal to 1. So the bra is n summation m is equal to 0 to infinity, alpha star to the power of m by root m factorial bra m. And therefore, if I try to find the inner product, which I will work out, there is an n squared summation m comma n equals 0 to infinity, alpha star to the power of m, alpha to the power of n by root of m factorial root of n factorial. The inner product of bra m with ket n, which is what I have got from there. But this is the Fock basis, this is a natural basis, and they are orthogonal states. So, I have a delta Mn, which means I can remove one of these summations. Perhaps I can remove the label m, replacing all m's by n. But this quantity is simply n squared summation n equal to 0 to infinity modulus of alpha to the power of 2n by n factorial. And if this object is normalized to 1, this implies that 1 is equal to n squared, and this is the familiar exponential series. Exponential of mod alpha squared, and therefore n squared is e to the minus mod alpha squared, and n is e to the minus mod alpha squared by 2. So, I have fixed the normalization, it is e to the minus mod alpha squared by 2, and therefore the normalized state, this is the coherent state. It is called a coherent state because it satisfies certain properties. There is spatial coherence and there is temporal coherence. For the moment, I would choose to call ket alpha as a coherent state. So, ket alpha normalized is e to the minus mod alpha squared by 2 summation n equals 0 to infinity alpha to the n by root n factorial ket n. This infinite superposition has some very interesting properties. Let me find out the action of A on the state ket alpha. This is e to the minus mod alpha squared by 2. I can well take the operator inside the summation. I would like to pull out the first term corresponding to n is equal to 0, because that is alpha to the power of 0 root of n factorial a on ket 0, and that is a 0 because a on ket 0 is 0, and therefore I am left with this object I have used the property that A annihilates the 0 photon state. In the case of the simple harmonic oscillator, A acting on the vacuum state gave me 0. So, the vacuum state in the case of the simple harmonic oscillator, the ground state of the simple harmonic oscillator, equivalently in this problem the 0 photon state is an eigenstate of the annihilation operator with eigenvalue 0, because I can well write it in this manner. It is a trivial eigenstate of the annihilation operator, trivial in the following sense that the eigenvalue is simply 0. And therefore, I have A acting on ket alpha is e to the minus mod alpha squared by 2. I can pull out an alpha, summation n is equal to 1 to infinity alpha to the n minus 1, because I have pulled out alpha, by root of n factorial. A acting on n is root n ket n minus 1. This object A acting on n is root n ket n minus 1. It is easy to see what the answer is going to be on simplification. I can replace n minus 1 by m, so that the summation goes from m is equal to 0 to infinity, and therefore, A acting on ket alpha is alpha e to the minus mod alpha squared by 2 summation m equals 0 to infinity alpha to the power of m, because there is a root n there and a root of n factorial here, gives me a root of n minus 1 factorial in the denominator, which is the same as root m factorial, and that is a ket m. But this is the same as the coherent state ket alpha. And therefore, I have shown that alpha, ket alpha, is an eigenstate of the operator A with eigenvalue alpha, where alpha can be any complex number. I have not imposed any conditions on the value of the number alpha. So, you see, I have an eigenstate, another eigenstate of the annihilation operator apart from the 0 photon state, and this is an infinite superposition of photon number states. It is non-trivial in the following sense that the eigenvalue is a non-zero number in general. So, this is an annihilation operator eigenstate with further interesting properties. For instance, I could find out the mean photon number in this state. This is identical in my notation to an object A dagger A within this bracket. So, what is the mean photon number in the state alpha? Since A acting on alpha is alpha alpha, it is clear that if I take the Hermitian conjugate, I would get this, and sandwiching that, therefore, I have alpha A dagger A alpha is an alpha star alpha inner product of the ket with the bra, and that is mod alpha squared, because that is normalized to unity. Therefore, the mean photon number in the coherent state is mod alpha squared, is equal to mod alpha squared. But the mean photon number is the intensity of the light. Therefore, mod alpha squared essentially gives us the intensity of the light that is used. I would like to find out the fluctuation representing this by n. I would like to find out the fluctuation delta n in the number, but I know that delta n is expectation n squared minus expectation n the whole squared, delta n squared. The variance in n is expectation n squared minus expectation n the whole squared. Now, where A dagger A is simply given by n, that is my notation. So, let me compute these objects. You see, the expectation value of the operator n was mod alpha squared, and therefore, expectation value of n the whole squared is mod alpha to the power of 4. I need to compute expectation n squared, but that is the same as doing this. N is A dagger A, and I should remember that there is a careful ordering that needs to be maintained here. This is quantum mechanics. I cannot write this as A dagger squared A squared. I cannot pull this across A, because I know that there is a non-trivial commutation relation between A and A dagger. They do not commute with each other. So, I could write this as alpha A dagger. A dagger is 1 plus A dagger A, and then there is an A from here. So, this quantity is alpha A dagger A alpha, that is my first term, that is an A dagger and an A there, and I have an alpha A dagger squared A squared from the next term. But this I know is mod alpha squared, and this I know A squared on ket alpha gives me alpha squared, and A dagger squared on bra alpha gives me alpha star squared. Therefore, this gives me mod alpha to the 4, and therefore, I know the variance in the photon number. So, delta n squared is expectation A dagger A squared minus expectation A dagger A the whole squared, which is mod alpha squared plus mod alpha to the 4 minus mod alpha squared minus mod alpha to the 4, and that is equal to mod alpha squared. Now, this is an interesting result because the mean is equal to the variance, equal to mod alpha squared, which is typical of a Poisson distribution. This is a Poisson distribution, has mean equal to variance. I could do better. I could find out the probability of detecting m photons in the state ket alpha. Since ket alpha is an infinite superposition of photon number states, the normalized state is given by this. The probability of detecting m photons in the state alpha is given by Pm of alpha, and it is clear that Pm of alpha is simply m alpha mod square. You will recall from the probabilistic interpretation of quantum mechanics that indeed the probability of finding m photons in this state would be to take the inner product of m with alpha and then mod square it. That should pull out the weightage given to the state ket m here and mod square it. So, this quantity is simply e to the minus mod alpha squared by 2 summation n equals 0 to infinity alpha to the n by root n factorial mn mod square. This is delta mn because of orthogonality. Therefore, I have Pm of alpha equals e to the minus mod alpha squared. I have already squared this, summation n equals 0 to infinity. The summation goes because of the delta mn, and I just have alpha to the m by root m factorial mod square alpha star to the power of m by root m factorial, and that is all that I have. This quantity, the delta mn, changes all n to m, replace all n by m, remove the summation and mod square. The mod square means the complex conjugate has to multiply this, but that is the same as e to the minus mod alpha squared mod alpha squared to the power of m by m factorial. So, if I just denote mod alpha squared by nu, Pm of alpha is e to the minus nu to the power of m by m factorial, which is typical of a Poisson distribution. So, this is a Poisson distribution in nu. And this is the kind of result that can be tested in principle with ideal laser light, which is represented by the coherent state ket alpha. When I am at this, I also wish to find out the uncertainty in x. X is a plus a dagger by root 2, and we should remember that x is not position in this context. X is really related to the electric field E. So, I want to find out the variance in x, where x is a plus a dagger by root 2 in the state ket alpha. So, essentially I need to find expectation x squared minus expectation x the whole squared. So, let me begin with expectation x squared. X squared, even from the last lecture, is simply a squared plus a dagger squared plus 2 a dagger a plus 1, because in x squared you would have had an a dagger plus a dagger a, and I use the commutation relation and get this. Therefore, alpha x squared alpha is half alpha a squared alpha is the first term plus alpha a dagger squared alpha, that is the next term, this is what I have. And therefore, expectation x squared in the state alpha, A acting on alpha pulls out alpha as the eigenvalue, and therefore, A squared acting on alpha gives me alpha squared ket alpha, but the inner product of ket alpha with bra alpha is 1, and therefore, I am left with the number alpha squared. The second term is a dagger squared. I could work with a dagger acting on bra alpha, that pulls out an alpha star, twice over gives me alpha star squared, and use the fact that the inner product of ket alpha with bra alpha is 1, therefore, I get alpha star squared. Equally well, you could have realized that this object is the complex conjugate of this object. Therefore, if the expectation value of a squared is alpha squared, the expectation value of a dagger squared is alpha star squared, plus A acting on ket alpha is alpha ket alpha, and a dagger on bra alpha is alpha star. There is a 2 out here, so that gives me plus 2 mod alpha squared plus 1, simply because this object is 1. So, this is expectation x squared. Expectation x is simply 1 by root 2 alpha a plus a dagger alpha, which is 1 by root 2. The first term is the expectation value of a, the second term is the expectation value of a dagger. And this is clearly alpha plus alpha star. I need expectation x the whole squared, that gives me a half. When I square this, I get alpha squared plus alpha star squared, and since alpha and alpha star are just numbers, I have 2 mod alpha squared. I need to subtract expectation x the whole squared from expectation x squared. Which gives me the variance in x. In this object, so when I subtract expectation x squared from expectation x squared, first term vanishes, so does the second term, and so does the third, but what survives is a half. And therefore, in units where h cross is equal to 1, delta x squared is equal to half. The variance in x is half in the coherent state ket alpha. This is analogous to the ground state of the oscillator, equivalently the 0 photon state. where in units where the Planck's constant is set equal to 1, delta x squared is equal to half. Now let me compute the variance in P. Again, P in this context is related to the magnetic field and is not to be confused with linear momentum. I emphasize the fact that while the model, the framework that we used in terms of A and A dagger and the Hamiltonian, the framework is the same, be it the simple harmonic oscillator or the quantized electromagnetic field. The interpretations, the physical interpretations are different, and P is defined as A plus A dagger, A minus A dagger by root 2I. I need to find P squared, and that is a minus half A minus A dagger the whole squared. And if you recall, this is A squared plus A dagger squared minus, there is an A dagger A minus A dagger, so that is a minus 2 A dagger A plus 1 in the bracket. Because A dagger can be written as 1 plus A dagger A, and that is how I got this. So this is P squared. I need to find the expectation value of P squared in the state alpha. So expectation value of P squared in the state alpha, that is the same as this object. This quantity is alpha. There is an overall factor of minus half. So that is a minus half A squared plus A dagger squared minus 2 A dagger A minus 1 alpha. Now once more, as before, the first term gives me alpha squared, the second term gives me alpha star squared in the expectation value, the third gives me minus 2 mod alpha squared, and the fourth gives me a minus 1. There is an overall minus sign, and therefore this just gives me 2 mod alpha squared minus alpha squared minus alpha star squared plus 1, half of that. So this is expectation value of P squared. Need to find expectation value of P and square it, which is what I will do now. The expectation value of P in the state alpha, my notation is this, is 1 by root 2I alpha A minus A dagger alpha. This object is 1 by root 2I. The first term is alpha and the next term is alpha star with a relative negative sign between them out there. So expectation P the whole squared is half with a minus sign alpha minus alpha star the whole squared, which is minus half alpha squared plus alpha star squared minus mod alpha squared with the 2. I need to find the variance in P. Delta P the whole squared, that is the variance, is expectation P squared minus expectation P the whole squared. Look here for expectation P squared, there is a minus alpha squared by 2 minus alpha star squared by 2. This gives me, once I put in this minus sign, it cancels out with an alpha squared by 2 here and an alpha star squared by 2. Similarly, I have a mod alpha squared out here with a plus sign. Here I have mod alpha squared, but now with a negative sign because I am subtracting expectation P squared from expectation P the whole squared. And therefore, this object is simply the half that I had when I found the expectation value of P squared. That was the last term with a half. So, what we have established is that delta x squared, delta p squared, they are both equal to each other and equal to half in units where the Planck's constant is set equal to 1. This is precisely what happened with the ground state of the harmonic oscillator. It is precisely what happened with the 0 photon state. In other words, the coherent state is also a minimum uncertainty state in x and p, where x and p are not to be misunderstood in this context as position and momentum. So, in the canonical variables x and p, the coherent state also is a minimum uncertainty state. One starts wondering if there is any way in which we can use a suitable operator, act a suitable operator on ket 0 to get ket alpha. In other words, I wonder if there is a unitary transformation which takes ket 0 to ket alpha, and indeed that is true, and without making much ado about it, I will first give you the unitary operator, and then we will see how exactly this unitary operator takes ket 0 to ket alpha. Consider the operator d of alpha given by e to the minus mod alpha squared by 2, that is a number, e to the alpha a dagger, e to the minus alpha star a. Consider this operator. The order is very important because a and a dagger do not commute with each other. Let me find out the action of d of alpha on ket 0. The overall number is the same, it is e to the minus mod alpha squared by 2, e to the alpha a dagger, e to the minus alpha star a acting on ket 0. I emphasize that this exponential series is of the form 1 minus alpha star a plus minus alpha star a the whole squared by 2 factorial plus so on. So, it is a sum of a series of operators where the first term is the identity operator acting on ket 0. Well, I know that a acting on ket 0 is 0 and here too a squared on ket 0 is 0. So, every term here acting on ket 0 simply destroys it. What survives in e to the minus alpha star a acting on ket 0? Simply the leading term, the identity operator acting on ket 0. So, this object is e to the minus mod alpha squared by 2, e to the alpha a dagger, ket 0, because the identity operator alone gives me ket 0 and all other operators in that series act on ket 0 to give me 0, the number 0. Now, this object can be evaluated. So, d of alpha acting on ket 0 is e to the minus mod alpha squared by 2. I have 1 plus alpha a dagger plus alpha squared a dagger squared by 2 factorial plus so on acting on ket 0. That is an infinite series of operators acting on ket 0. Well, the leading term is ket 0. I have an overall constant e to the minus mod alpha squared by 2. The leading term is ket 0. A dagger on ket 0 is root 1 ket 1. I would like to keep the root 1 there explicitly so that a general formula emerges for this infinite set of operators acting on ket 0, plus alpha squared by 2 factorial. The first time a dagger acts on ket 0, it pulls out a root 1, gives me ket 1. Then a dagger acts on ket 1 to give me root 2 ket 2 plus so on. And now the structure is clear. This is e to the minus mod alpha squared by 2 ket 0 plus alpha root of 1 factorial ket 1 plus alpha squared by 2 factorial root of 2 factorial ket 2 and so on. This is really e to the minus mod alpha squared by 2 summation n is equal to 0 to infinity alpha to the power of n by root n factorial ket n, because that gives me a root 2 factorial in the denominator. This could be written as a root 1 factorial in the denominator. The next term will give me a root 1 into root 2 into root 3 in the numerator. The denominator will have a 3 factorial, therefore I pull out a root 3 factorial in the denominator and so on. So this is what I have, but this is simply the coherent state ket alpha, and therefore I have an operator which acts on ket 0 to give me ket alpha. The operator is of this form. It is called the displacement operator. It is called the displacement operator because it displaces ket 0, takes it to ket alpha. One sees this better in the position representation, which I have not yet attempted to do, but in subsequent lectures I will show that if I give a position space representation for ket 0, it would be a Gaussian, and for ket alpha it would be another Gaussian which is simply displaced from the original Gaussian. So d of alpha is called the displacement operator. I have very carefully split and written d of alpha. In general, there is a disentanglement relation which says that if you have two operators a and b and you have e to the a plus b, you could write this as e to the a, e to the b. The order is important, first e to the a, then e to the b, e to the minus half the commutator of a with b provided the commutator of a with b is not equal to 0. However, the commutator of a with b is equal to the commutator of b with b is equal to 0. Now, if these conditions are satisfied, you could write e to the a plus b, where a and b are operators, as e to the a, e to the b, e to the minus half commutator of a with b. You could equally write e to the a plus b as e to the b, e to the a, e to the plus half commutator of a with b. Let us look at this example. Consider e to the alpha a dagger minus alpha star a. Consider this operator. This is like capital A in my example, and minus alpha star a is capital B. The commutator of alpha a dagger with minus alpha star a is simply minus mod alpha squared a dagger with a commutator, and that is just mod alpha squared, because this gives me a minus 1, and therefore with that minus sign it gives me a plus 1, and that is in general not equal to 0. Now look at the commutator of a with b. Now this object is simply the commutator of alpha a dagger. I have just evaluated this here, and this is a number. So this is mod alpha squared identity operator, and since any operator commutes with the identity operator, the commutator of a with b in this example is 0. Similarly, you can see that the commutator of b with b is 0, because the commutator of alpha star a with mod alpha squared identity is also equal to 0. And therefore, I can split using this disentanglement relationship. I can split this and write it as e to the alpha a dagger e to the minus alpha star a, e to the minus half commutator of alpha a dagger with minus alpha star a, which is precisely what I have written here. So this object here is really e to the alpha a dagger minus alpha star a. I could have written it in this manner, or I could have used the disentanglement relationship and written it in this manner. The disentanglement relationship itself is one of a variety of formulae which belong to the Baker-Campbell-Hausdorff formula and variants of the Baker-Campbell-Hausdorff formula. So I have used one such specific formula in this case, and I have written the displacement operator as e to the alpha a dagger minus alpha star a, or I can pull out this e to the minus mod alpha squared by 2 and write it in this manner, which is what I have done. What I have shown is that the displacement operator acting on ket 0 gives me ket alpha as the resultant state. It is obvious that the displacement operator is a unitary operator. Because d dagger of alpha is e to the alpha a dagger minus alpha star a dagger, and I could have done this term by term. It's like taking the dagger of the identity operator plus alpha a dagger minus alpha star a dagger plus so on, and that's the same as 1 plus alpha star a minus alpha a dagger plus, which is the same as e to the minus alpha a dagger minus alpha star a. So d dagger of alpha is the same as d of minus alpha. If here I had simply changed alpha to minus alpha, I would have got e to the minus alpha a dagger plus alpha star a. But d dagger of alpha times d of alpha is identity, because it's exponential of minus an operator times exponential of plus the same operator. It is equally true that d of alpha, d dagger of alpha is the identity operator, and therefore this rings a bell. I seem to have done a unitary transformation. The unitary operator in this case is the displacement operator d of alpha. The unitary transformation has taken ket 0 to ket alpha. I could argue further and attempt to see if it is the same unitary operator that takes a dagger to a dagger minus alpha star and a to a minus alpha. Now, the reason why I might expect this to happen is because I know that a on ket alpha is alpha alpha, a on ket 0 is 0 ket 0, and therefore a minus alpha on ket alpha is 0 ket alpha. So I wonder if the transformation, the operator which transformed ket 0 to ket alpha also transforms a to a minus alpha and a dagger to a dagger minus alpha star. And as I have discussed in one of my earlier lectures, when a state transforms in the following manner, the operators which act on that state would transform with d of alpha, the same operator flanking it on this side and its inverse on that side, and since this is a unitary operator, d inverse is the same as d dagger. And indeed this is true. It is possible to show that the following identities are true, and that is something that I will work out in detail at a subsequent in a subsequent lecture. But before that, I'd like to look at the orthonormality properties of coherent states. In particular, what is this object? Now, alpha is a label for a coherent state, and alpha can be any complex number. So, if I take two coherent states, one of them with the label alpha and the other with the label beta, then what is the inner product of alpha with beta? If they are orthogonal to each other, the answer would be 0, and if they are not, then I will have a non-zero value for the answer. So, let me look at this. Ket alpha is e to the minus mod alpha squared by 2, summation n equals 0 to infinity, alpha to the n by root n factorial ket n. Therefore, the bra is this object, and ket beta is e to the minus mod beta squared by 2. I will use a different index for the summation so as to avoid confusion. It is the same Hilbert space that I am looking at. The Fock basis or the number state basis or the natural basis is given by the label ket m or ket n, where the label takes value 0 to infinity, starting from the 0 photon state upwards. The combination itself, alpha and beta, are different because mod beta squared and mod alpha squared are different. The mean photon number in this state is mod alpha squared, the mean photon number in that state is mod beta squared. And now I wish to find the overlap, the inner product of alpha with beta. So, this has a mod alpha squared by 2 e to the minus mod beta squared by 2. There are two summations. And since there was a bra alpha, there is an alpha star to the n, beta to the m by root n factorial, root m factorial, bra n ket m, and as before this gives me a delta nm, which means I can remove one of the summations and perhaps replace all m's by n's. Alpha star beta to the power of n by n factorial, and that is all I have. I need to simplify this. Now, let me consider alpha beta mod square. Now, that object is e to the minus mod alpha squared, e to the minus mod beta squared, and summation n is equal to 0 to infinity alpha star beta to the power of n by n factorial times summation m equal to 0 to infinity alpha beta star to the power of m by m factorial. To understand what this could be, let me look at the expression for e to the minus modulus of alpha minus beta the whole squared. Now, this object is e to the minus alpha minus beta times alpha star minus beta star, which gives me e to the minus mod alpha squared from the first term, mod beta squared from the second term, minus beta alpha star minus alpha beta star. So, I can easily see that I have e to the beta alpha star plus alpha beta star here, apart from e to the minus mod alpha squared, e to the minus mod beta squared. So, that is an e to the minus mod alpha squared, e to the minus mod beta squared, and I have e to the beta alpha star plus alpha beta star. And indeed, this object turns out to be equal to that. And therefore, it is easy to verify that this double summation out here, summation over n, summation over m, is precisely this. Therefore, modulus of alpha beta the whole squared is e to the minus modulus of alpha minus beta the whole squared. Now, one thing is clear. Let us imagine for a moment that alpha and beta are real and beta equal to minus alpha and alpha large. Then alpha beta mod squared is e to the minus, that gives me an alpha minus minus alpha, and therefore that is a 4 mod alpha squared, and for alpha large it is 0, because that is like e to the minus infinity. And therefore, these two states ket alpha and ket beta, which are not orthogonal to each other, can be approximated to being orthogonal to each other, provided beta is taken to be minus alpha and alpha itself is large. I have already spoken to you about qubits in quantum computation. We spoke about spins, and there we had qubits in terms of which quantum computation and quantum logic gates could be constructed. This is another example. There have been attempts to use two coherent states of this type such that they can be considered to be orthogonal to each other to a fairly good approximation, and use them as the two qubit states. Instead of the column vectors 1 0 and 0 1, we have here ket alpha and ket beta satisfying these conditions, so that quantum logic gate operations can be implemented using these as qubits. Now, this is an area of a large amount of interest in current day research. This lecture is meant to give you a flavor for what an infinite superposition of states can do.